Hi, welcome to my channel, Math Made Easy with Laurel. In this video, we're going to talk about how we find future value and payment amounts for ordinary simple annuities. In my last video, I talked about what an ordinary simple annuity is, and just to review that, an ordinary annuity means that payments are made at the end of the interval, not at the beginning. And simple annuities are annuities where the number of payment periods per year is equivalent to the number of compound periods per year. In my last video, I showed how to find the future value of the annuity by finding the future value of each payment. However, in this video, we're just going to take a look at the formula for doing it because that's much easier. With annuities, we're working with compound interest. So the formula is going to look similar to what we've done in the past with compound interest. And the formula looks like this. Future value will equal the payment amount times, in brackets, 1 plus r over n, where r is the annual interest rate and n is the number of compound periods per year, raised to the power of n times t, where t is the time in years, minus 1 over r divided by n. You might see a formula that looks a little bit easier than this. I'm going to show you how they got it. If we take r over n and replace it with I, that simplifies this formula to 1 plus I, and I is in the denominator. And what this I represents is the interest rate per compound period. So I, which is equal to r over n, is going to be the interest rate per compound period. The other substitution we can do to make this look a little bit easier is let capital N represent small n times t. Number of compound periods per year times the number of years. And when we do that, we're going to get the total number of compound periods. If you prefer to use this formula, that's fine. Just be careful when you find I that you don't round it off. If it works out to something even, there's not going to be a problem. But if it's not an exact number, you've got to store it in your calculator and use that in your formula instead of the rounded off number. I'm going to use the original formula because I like to keep it exact, and I can keep it exact by doing all the calculations all at once. Let's take a look at some examples. We want to find the future value of $1,000 at the end of each year if it's earning 6% compounded annually and it's invested for 3 years. So we did this example in the last video, and I did it manually where we found the future value of each of those $1,000 payments. This time we're going to use the formula. If we set up a timeline, we can just write our timeline with the information from the question. We're earning 6% compounded annually, and our payments are $1,000 per year, or $1,000 yearly payments at the end of the year. Now let's list what values we know. We know the payment is $1,000. We know the interest rate is 6%, as a decimal is 0.06. We know the number of compound periods per year, because it's compounded annually, is just 1, and the time is 3 years. So let's plug these values into our formula. So we'll have $1,000 times, in this bracket I will have 1 plus r divided by n is just 0.06, to the power of n times t, which is just 3, minus 1 divided by r divided by n, which is 0.06. Understand order of operations and how you use your calculator properly to calculate this. And you should get a value of $3,183.60. In our second example, it says you are 20 years old and invest $250 at the end of each month. Okay, that makes it an ordinary annuity. Until you are 65 years old. Find the future value if a fixed rate of 9% compounded monthly is possible. We know this is simple because it's compounded monthly and you're making monthly payments. So we're going to use this formula, and when we set up a little timeline, we can see what's going on. So today it's 0. You're investing $250 a month at the end of each month. Its interest rate is 9% compounded monthly, and from 20 years old to 65 years old is 45 years. So let's take a look at the future value of this annuity. Payment is $250. Interest rate is 0.09. N number of compound periods, if it's monthly, there are 12. and the number of years is 45. So let's plug these values into our formula, and we get 250 times 1 plus 0.09 divided by 12 to the exponent of n times t, or 12 times 45, minus 1 over r divided by n. Let's simplify this before we use our calculator. 0.09 divided by 12 is exactly 0.0075. And then when I add that value to 1, I get 1.0075. And let's replace 12 times 45 with 540. Now, you're not going to always be able to simplify before you put it into your calculator. In this case, I'm just trying to make it look a little simpler. Now we plug this whole thing into our calculator, and we get a future value of $1,851,219.62. In our next example, Sam has $25,000 in an investment. He then contributes $3,000 at the end of each year for 4 years. How much is the investment worth at the end of 4 years if he is earning 5% compounded annually? So in this situation, we have a present value that's going to grow, and then the annuity payments that are going to grow. So we're going to calculate this future value of this separately and add it in. Setting up a timeline, we have $25,000 that's going to grow in 4 years. And in addition, we've got these payments made yearly at the end of each year. So we know it's an ordinary annuity. And because we're making yearly payments and it's compounded annually, it's an ordinary simple annuity. So let's first of all find the future value of this amount at the end of 4 years. We take our present value, multiply by 1 plus r over n, which is just 0.05, to the 4 times 1, which is 4. That gives us a future value of $30,387.66. Now let's use our formula to find the future value of all of our $3,000 annuity payments. List the values that you know and then plug them into your formula. And we get 3,000 times 1 plus 0.05 over 1 is just 0.05. N times t is just 1 times 4, or 4. Minus 1 over r divided by n is 0.05. Now let's calculate this. And we get $12,930.38. To find the total future value, I add those two amounts, and I get $43,318.03. If you were just to add these two values on your calculator, you would get $43,318.04. However, I kept the actual values on my calculator. I wrote them down, rounded off, but I didn't round anything off while I'm doing calculations. Now let's use this same formula, and this time we're going to know the future value, and we're going to calculate what the payment needs to be. So our next example says you need $20,000 in 5 years for a trip. How much should you set aside monthly to have sufficient funds if your investment can earn 8% compounded monthly? We're going to make the assumption that that investment starts a month from now, and so that makes it an ordinary annuity. And if the compounding is monthly and you're putting monthly payments, that makes it simple. So let's set up a timeline. So this example is different than the previous examples because we know the future value. We want to have $20,000 in 5 years. We know our interest rate. We don't know the payment. We can solve for the payment because we know all of the other values in this equation. So let's start by plugging these values in. So we have 20,000 equals payment times this amount here. Again, we can simplify 12 times 5 before we start and write 60. 0.08 divided by 12 is not an even number, so we're going to leave it in fraction form. 2 ways you can solve this. To isolate for the payment, you can divide $20,000 by this whole expression, or you can find this value, and once you've got one value, then you can divide 20,000 by it. Just be careful that you don't round anything off when you're doing that calculation. I'd like to make a suggestion that if you do calculate this first, when you get your result, store it in the memory on your calculator. Then you can go 20,000 divided by recall that memory equals. If you do it correctly, you should get $272.19. In our last example, it says Lucy wants $1 million in an annuity by the time she retires in 35 years. If the annuity pays a fixed interest rate of 4.5% compounded monthly, how much should she deposit at the end of each month into this account? So if we set up our timeline, starting today and going to 35 years, we want a future value of $1 million. The interest rate as a decimal is 0.045. The number of compound periods per year is 12, and the number of years is 35. Plugging these values into our formula, we're going to proceed just like we did with our last example. So we get 1 million equal to a payment times this whole expression, which we can put into our calculator and get one number, and again stored in the memory. Then we're going to divide 1 million by that value to get our payment. Lucy needs to make payments of $982.57 per month for 35 years if she's obtaining this interest rate, so that she ends up with a future value of $1 million. In the next video, I'm going to show you how you find present value of annuities. In my next video after that, I'm going to show you how you can use your business analyst calculator, in other words, these white keys, to do all of the questions in this video and the next. See you then.